Hello folks, how is it going? Mike coming back at you here with another video on number theory. In the previous video, we introduced the Euclidean algorithm. We saw what the method is. We saw how to figure out what the greatest common divisor of two numbers is, and we went through one sample problem. The Euclidean algorithm, once again, is really just a repeated use of the division algorithm that we learned about in a previous video. And when we get to the next use of the division algorithm, we're just changing the places of some numbers here. So in this video, we're going to go through a few more sample problems. We'll do a couple together, and then I'll leave you a couple to solve on your own, and we'll see if you got those right. But first one up here, we're going to find the GCD of 5,720 and 855. So we're going to be finding GCDs of larger numbers here. 3 digits, 4 digits, 5. In this video, we'll see one where we have a 6-digit number as well. But with this one here, if we look at the numbers that we have our A value of 5,720. Again, we typically go with A being the larger number, and then our smaller number B is 855. So what we're going to do is we're going to use the division algorithm to write A as some whole number times B plus some remainder, and that remainder R, pardon me, is less than B. So the question here really is, how many 855s can I pull out of 5,720? Well, if you just check on your calculator, if you try to do 5,720 divided by 855, you'll be left with 6 point something afterwards. So we can pull 6 855s out, and we are left over with 590. So I can write 5,020 as 6 times 855 plus 590. This is my A value, this is my B value, and this is my R value. We go through another use of the division algorithm. The B value, 855, in the next row down, is going to take the place of my A, which I have here. That doesn't look like an A. And then my R value is going to take the place of my B value. So now we're thinking, okay, how many 590s can we pull out of 855? We can pull exactly one 590 out of 855, and we are left over with 265. So 855 is 1 times 590 plus 265. Once again, we're going to use the division algorithm. Things are changing places once again. 590 is going to become my new A. The 265 is going to become my B value here. And we keep going through this process. We can pull two 265s out of 590 and be left over with 60. We go once again with the division algorithm. Again, note what's in the place of B is taking the place in the next line for A, and then my remainder R in the next line is taking the place of where my B would be. So 265 is 4 times 60 plus 25. The 60 moves into the spot of A. The 25 moves into the place of B. 60 is 2 times 25 plus 10. Once again, moving things over. 25 is 2 times 10 plus 5. We're done with the Euclidean algorithm when we get a remainder of 0. So we still have to go at least one more. But when we do go one more, 10 is 2 times 5 plus 0. So now we are completely done with our algorithm. We can now determine what is the GCD of 5,720 and 855. Thinking back to the previous video, we said that the last non-zero remainder that we have, that is to say, in this case, the 5, the last non-zero remainder is the GCD of your two given numbers. So 5 is the GCD of 5,720 and 855. So that's how we figure out, this is just one more sample of seeing what is the GCD of these two numbers. We'll go on to another sample. We're going to be working with some even larger numbers in this sample problem. And this is an example where we'll see that finding the GCD can take some time. It can take a lot of steps to figure out finally what your GCD is going to be. Now, obviously, for the sake of homework or quizzes or tests, we are not going to be going through problems that are this long. You will not have to do you will not have to use the Euclidean algorithm and have to go through this many steps. It's just too time consuming and it's unnecessarily long. But since this is just practice, I'll show you what one of these nastier guys looks like. Let's find the GCD of 171,990 and 53,482. Again, first number is A. Second number, the smaller number, is B. We write A as Q times B plus R. So how many 53,482s can we pull out of 171,990? We can pull 3 of them out, and we're left over with 11,544. Again, my B value is going to take the place of my A value in the next line down, and my R is going to take the place of my B value. And when we do that, 53,482, we can pull 4 11,544s out of that, and we're left over with 7,306. Okay, our remainder is not 0, so we keep going on with this process. B becomes the new A, R becomes the new B. And I'm going to skip through most of the steps. There are a lot of uses of the division algorithm here when solving this particular problem. We can pull 7,306 out of 11,544, and we're left over with 4,238. Now, how many 4,238s can we pull out of 7,306? We can pull 1 out, and we're left over with 3,068. Again, following the same pattern, you can see we're doing this several more times. The last step I left off with here is 156 is equal to 1 times 130 plus 26. Pause the video here if you want to actually go through these extra steps here and just see how we're getting down to this last line that we are. Keeping it in mind that to form the next line, the B value becomes the new A value, the R value becomes the new B value. So our remainder is not 0 here. The last remainder that we found is not 0, that is. So we have to use the division algorithm once again. 130, how many 26s can we pull out of 130? Well, we can pull 1 second. How many 26s can we pull out of 130? We can pull exactly 5 out. And we have a remainder of 0. So now our Euclidean algorithm is done. So what is our GCD of 171,990 and 53,482? Well, the Euclidean algorithm says that the GCD is the last non-zero remainder, which in this case is 26. So the GCD of these two large numbers is 26. Now, obviously, what we learned well before high school is if you wanted to find the GCD of two numbers, you would list out all the you'd list out all the factors of each number, and you would find the largest factor that each number has in common. Well, you can't easily do this, obviously, for these large numbers, for 5-digit numbers, as well as for 6-digit numbers. So this is a really nice way to calculate what the GCD for these large numbers are. So those were a couple problems that we went through together. Next up are a couple that I want you to try on your own. First up, try on your own to find the GCD of 56,800 and 3,740. So use the Euclidean algorithm here. Try to find the GCD on your own. Think about the process that we are going through. So pause the video now, and once you think you have it, press play, and we will see if you got it. All right, so let's see if you came up with the correct answer. This is what your Euclidean algorithm should have looked like. You can pull 15 3,740s out of 5,680, and you're left over with 700. You can then pull 5 700s out of 3,740 and be left with 240. You can pull 2 240s out of 700 to have 220 left over. You can pull 1 220 out of 240 and have 20 left over. And then you can get exactly 11 20s out of 220 and have nothing left over. So by the Euclidean algorithm, our GCD is 20. So hopefully you came up with 20 as the GCD of 56,800 and 3,740. Next problem, to try on your own, try to find the GCD of 2,431 and 210. This one will take a little bit longer. There will be a few more steps involved in this Euclidean algorithm, but it's still not too bad to figure out what the GCD is going to be. So pause the video here. Once you think you have the answer, press play and see if you were right. All right, so let's see how you did on this problem. You should have come up with a GCD of 1. Therefore, these two numbers are relatively prime. Just to go through the first couple steps here, you can get exactly, or you can get 11 210s out of 2,431, and you're left with over with 121. Then you get one 121 out of 210, and you're left over with 89. Following down in this same sequence of steps here, you have 7. You can get 1 4 out of that and have 3 left over. You can pull 1 3 out of 4 and have 1 left over. And then you can get exactly 3 1s out of 3 and you have 0 left over. But our last non-zero remainder is the 1. So that is our GCD. So these were just a few sample problems getting us more practice with finding the GCD of 2 numbers. And this is a really, really powerful way to come up with the GCD for any size of numbers whatsoever. They could both be 2 digits, or we could have a 2-digit and a 3-digit. Or as we saw in this video, we can have a 6-digit and a 5-digit number. A really, really simple, straightforward, yet powerful method to calculate the GCD of 2 numbers. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.